Hi, I'm Dr. Abhishek Joshi, and in this video lecture I'm going to discuss about the effect of the temperature on the avalanche gain and the photodetector or the receiver source of noise. So in this lecture we will be discussing the effect of the temperature, the effect of the noise and the noise produced by the photodetector side. So let's start lecture. So in this we will be discussing about the effect of the temperature on the avalanche gain. These are the contents. The comparison of the photodetectors, then the photodetector receiver source of noise, and finally we will be concluding with the signal to noise ratio calculations. So the effect of temperature on avalanche gain. So a small change in temperature can cause large variation in gain. So if the operating temperature decreases and the applied voltage is constant, ionization rate increases, so will avalanche gain. So to maintain the constant gain, the electric field in the amplifying region of the PN junction diode must also change, and this requires compensation circuit which adjusts the applied voltage on the photodetector when the temperature changes. So the temperature dependent expression is given by M, that is equals to 1 by 1 minus V by VB, and VB is the biasing voltage raised to power N, and V is the applied voltage. So as we can see in this figure, the breakdown voltage is also dependent on the temperature given by the expression, that is the bias voltage at a given temperature T is equals to the bias voltage at the initial temperature T naught, that is 1 plus A T minus T naught, or it can be given in terms of the refractive index N, that is with respect to temperature the refractive index is changing, that is NT, that is equals to NT naught 1 plus B T minus T naught. So this is the example of how the gain mechanism of a silicon avalanche photodiode depends on temperature, and the measurements of this device were carried out at 825 nanometers. So here we can see we are having the current gain on the y-axis and the voltage on the x-axis, and it is ranging from 0 to 400, and the current gain is ranging from 0 to 1000. So we are having the silicon of N plus P pi P plus and the avalanche photodiode. As we can see in the figure, the initial voltage that is ranging from 0 to 50. So from 0 to 50 volt, there is no change. All are behaving the irrespective of the temperature. It may be a 0 degree temperature, it may be 23 degree temperature, it may be 43, or it may be 67. So when we are talking about 0 degree, so we can see that the current gain is following this curve. When we are talking about the temperature of 23 degrees, the gain curve is slightly down and the gain is slightly decreasing. So current gain is decreased by some quantity. When we are talking about the voltage is increased more, and we are talking about the temperature 43. So again the current gain is slightly decreased. And when we are talking about the 67 degree temperature, the current gain is also decreasing. So here we can see the comparison of the photodetector, because we know that the photodetector may be made up of different semiconductor material. It may be a silicon, it may be germanium, it may be indium gallium arsenide. So this section summarizes some generic operating characteristics of silicon, germanium and indium gallium arsenide photodiodes. So this table shows the list of performance values of PIN and avalanche photodiode respectively, and the values were derived from the various vendor data sheet and from the performance number reported in the literature. So they are given in the guidelines for comparison purpose, and detailed values on specific devices for a particular application can be obtained from the photodetector and the receiver module suppliers. So here we are having the general or you can say the generic operating parameters of silicon, germanium, indium gallium arsenide, PIN photodiodes. So here we can see we are having the wavelength range given by lambda, and wavelength ranging for silica is 400 to 1100. For germanium it is 800 to 1650. For indium gallium arsenide it is ranging from 1100 to 1700. When we are talking about the responsivity, that how much response will be provided in amperes per watt. So for silicon it is ranging from 0.6 to 0.4 to 0.6. For germanium it is ranging from 0.4 to 0.5. For indium gallium arsenide it is ranging from 0.75 to 0.95. When we are talking about the dark current, that is ID in nanoamperes, thus for silicon it is ranging from 1 to 10 nanoamperes. For germanium it is that is 50 to 500 nanoamperes. For indium gallium arsenide it is ranging from 0.5 to 2 nanoamperes. The rise time, that is tau r in nanosecond, is given by 0.5 to 1, and for germanium it is 0.1 to 0.5, and for indium gallium arsenide it is ranging from 0.05 to 0.5. When we are talking about the modulation bandwidth, it is given by BM, that is in gigahertz, and ranging from 0.3 to 0.7. For germanium it is ranging from 0.5 to 3, and for indium gallium arsenide the bandwidth is ranging from 1 to 2. When we are talking about the bias voltage required, for silicon it is 5 volt, for germanium it is 5 to 10 volt, and for indium gallium arsenide it is only 5 volt. So when we are talking about the avalanche photodiode, so these are the general operating parameter for silicon, germanium, indium gallium arsenide avalanche photodiode. So the wavelength is ranging from that is for silica, germanium and indium gallium arsenide ranging from 400 to 1100. For germanium it is 800 to 1650. For indium gallium arsenide it is ranging from 1100 to 1700. When we are talking about the avalanche gain or the avalanche multiplication, for silica it is 20 to 400. For germanium it is 50 to 200. For indium gallium arsenide it is 10 to 40. When we are talking about the dark current, that is ID in nanoamperes, for silica it is 0.1 to 1, germanium 50 to 500, indium gallium arsenide is ranging from 10 to 50. When we are talking about the rise time, that is tau r in nanoseconds, it is ranging from 0.1 to 2, and germanium it is ranging from 0.5 to 0.8. For indium gallium arsenide it is ranging from 0.1 to 0.5. Now next important parameter is the gain bandwidth product. So gain here in the avalanche is nothing but the factor m, that is the avalanche multiplication, and the bandwidth is given by B. So the unit will be in gigahertz. So for silicon we are having the range of the gain bandwidth product, that is from 100 to 400. For germanium it is ranging from 2 to 10. For indium gallium arsenide it is ranging from 20 to 50. For when we are talking about the bias voltage, if we compare the silicon in volt, that is 150 to 400. For germanium it is 20 to 40. For indium gallium arsenide it is 20 to 30. So for the short distance application, silicon device operating around 850 nanometer provide relatively inexpensive solution for most links. Longer wavelength usually require the operation in the 1300 and 1550 nanometer windows. Here one normally used indium gallium arsenide based devices. So here we can see the photodetector receiver and its equivalent circuit. So in this we have the bias voltage. Here we are applying the bias voltage. So here this is the N side, this is a P side, N side, because we know that the photodetector is applied with the reverse bias voltage. So this is applied with the positive. Here this is applied with the negative. Negative means, or we can say that it's ground. So obviously it is reverse bias, and we can see we are having the external energy, that is the energy in form of light. The energy is given by E is equals to h nu, where h is the Planck's constant, nu is the frequency. So here we have the load resistance RL and it is connected to the amplifier. Now, what is the need of the amplifier? At the receiver side, we are getting very less number of the photons. So, due to the less number of photons, the energy which we have generated is very less. So, signals detected by the photodetector will be very less. So, we have to amplify these signals. So, once we have converted with the help of this transducer, we have converted the photons to the electron hole pair, we can generate the signals, or further this can be multiplied by the amplifier. So that's why we are using an amplifier. So this photodiode having the energy given by h nu, this is the photodiode, and it's having the diffusion capacitance that is given by CD and the series resistance that is RS. And the load resistance, here we can see we are having the load resistance. So this is the equivalent circuit. So here we have the load resistance RL. For the amplifier, we are having the resistance of an amplifier, that is RA, and the capacitance of an amplifier given by CA. And finally, it is connected to the amplifier, which is acting as an amplifying device for the electrical signals. So this is the simple model of the photodetector receiver and its equivalent circuit. So let us discuss the different noises present in the receiver, or we can say it is an error. So this figure shows the block schematic of the front end of an optical receiver and the various noise sources associated with it. So the majority of the noise sources shown apply to both. So here we have the optical signal having the energy h nu. Now we know the photodetection process means the optical signal will be converted to the electrical signal with the help of the photodetection process. So it may be PIN photodiode or it may be Avalanche photodiode. So depending on which type of photodiode we are using, it is sensing that light for a particular wavelength. So here also in the photodetection process also we are having the noise. The noise may be a quantum noise, or it may be the dark current noise, or the background noise, or the beat. A beat may be from the incoherent carriers. So if we are using the Avalanche photodiode, we have the Avalanche gain. So Avalanche gain is also having the noise. So this means the access due to the random gain mechanism. At the detector, we are having the detector load bias. So it is also having the noise. Here the noise will be in form of the thermal noise. Then next we have the amplifier. So amplifier is having the electronic gain, that is having it is also a part of the noise. This is the thermal. We are having the input resistance and the device with the active element and the surface leakage current. So surface leakage current we have. So these are the three main components of the noise in the electronic gain amplifier, which we have already seen in the various communication systems. So the output is the electrical signal. So this is the sources of the noise in the receiver, or you can say the optical receivers. So we can further calculate the signal to noise ratio, or the SNR ratio, that is signal to noise ratio. So SNR is important to know that how much signal power is there and how much noise power is present in our received signal. So we have the signal power from the photocurrent, because we are using the photodetectors, then divided by the photodetector noise power, plus the amplifier noise power. So we are having the photodetector noise power plus the amplifier noise power. To achieve the high signal to noise ratio, the following condition should met. So there are two conditions. First is the photodetector must have the high quantum efficiency to generate large signal power. Second one is the photodetector and the amplifier noise should be kept as low as possible. So photodetector noise is given by, that is eta q by h nu, that is multiplied by pt. So for a PIN photodiode, the mean square signal current, that is Is square, is given by, that is sigma s square pin and the photocurrent IP square T. So for avalanche photodetectors, Is square, that is a short noise square, is equals to the variance for the avalanche photodiode, that is APD. It is nothing but the photocurrent, the primary photocurrent square, that is I square, and the avalanche multiplication, that is given by M square. So the noise, noise current is given by In is the noise current, and its square is nothing but it is the power of the noise, or we can say the variance of the noise, that is sigma square. So it is a combination of different noise at it may be due to the dark current, it may be due to the short, or it may be due to the series. Okay, so it is the combination of sigma square for the short noise plus the sigma square for the dark. So here we are having 2q, that is q is the charge, IP is the photocurrent, ID is the dark current, M square is the avalanche multiplication factor, FM BE plus 2q IL, that is a leakage current, and multiply by BE. So the total current is given by I square, or it may be due to the thermal. So we are having sigma square T, that is given by 4k BT by RL multiplied by PE. So signal to substituting the values of the noise power and the thermal noise power, we are getting the total noise power here in the denominator. In the numerator, the signal power is nothing but the IP square into M square. So substituting the values in the numerator, we are having the source power or the signal power, that is IP square into M square, and the noise power is given by 2q IP plus ID M square FM BE plus 2q IL BE, this factor, and 4 times now this factor. So this factor is the thermal noise. Due to the thermal noise, we are having 4k B TBE by RL, where RL is the load resistance. Now signal to noise ratio that is further simplified as, that is IP square M square. So IP square is the primary photocurrent. This is the primary photocurrent. M square is the avalanche multiplication, and the new denominator is nothing but the noise, the power of the noise, that is given by 2q IP. IP is the primary photocurrent, M square FM BE plus 4 KB TBE by RL. So in this lecture, we have discussed about the effect of temperature on the avalanche gain, and we have seen that avalanche is similar to the flood, and we are achieving a gain, means the multiplication factor, means only 50. For example, we are having the 50 photons. Now this 50 photons, due to the avalanche multiplication, it is becoming 100 electron hole pair. So this means we are having the avalanche gain or the avalanche multiplication. Then we have discussed the comparison of the photodetectors. The comparison of the photodetectors are based on various parameters, that is for the PIN photodiode and for the Avalanche photodiode. And the parameters which we have used to compare is the wavelength range, the responsivity, the dark current, the rise time, and the modulation bandwidth, and the bias voltage. Next, we have discussed about the photodetector or the receiver source of noise. So, different noise present in the receiver. So, we have seen the different noise. It may be during the photo detection. It may be if you are using the Avalanche photodiode, we are having the Avalanche gain. If we are having the detector load bias, then the thermal noise will be there. If it is an electronic amplifier, then again noise is there. So, noise is present in each and every block of the system. Then we have calculated the signal to noise ratio. So, signal to noise ratio in communication is very important to analyze that how much signal power is there in the communication system. So, here we have covered all the major topics of the optical communication receivers, and we have covered the phenomena and the working of the photodiodes. So, here we have discussed the working principle of the photodetectors. So, in our next lecture, we will be discussing, we will be covering the next topics based on the free space optics, and how we can use the photo or the sources or the detector in a system, and we can use in the different applications of the communication system. So, here I am going to stop the lecture. Thank you.